Hi everybody. I did a very silly thing and I forgot to record audio when I was recording my office hours. So what you're seeing now is me talking to people in office hours while I'm recording the audio for this later. And probably what I'm talking about right now, so there's going to be some disjointed kind of communication happening here. But probably what I'm talking about right now is the fact that you should all attend office hours, because even though all of us instructors are planning on recording our office hours, it's not always going to go the way that we plan. You should be working on having about 12 hours of chemistry work a week. And the best way to do that is to have 2 to 3 hours of chemistry work a day, rather than trying to do it all on the Friday when everything is due. Since I don't remember the other things I said, I'll just go ahead and give some other tips and advice as well. I would encourage you all to, while you're doing your LabPal assignments, to write down what you did, so that way when you are looking at the LabPal assignments later, you can tell how you got the right answer. The quizzes and everything that we'll be doing at the end of the week will depend on you having an understanding of how you got right answers on these other aspects. Something else that I'll mention, I'll talk about the Canvas page a little bit. I was probably doing some screen sharing in there, which won't be recorded. When I record office hours, I'll always be using a secondary camera, which is part of what created this audio hiccup. But that way your faces will never be recorded or shown. Your voices will be recorded and shown though. So some things that I mentioned about the Canvas page during office hours is, on that home page, you'll see kind of at the top, you'll see the instructors you can email in their office hours, and the times on those are the links to our different Zoom offices. And since you need to do about 12 hours of work a week, I strongly encourage that you actually come to office hours even if you don't have questions. That way you can just show up, you can have a set time where you're going to work, and then if something goes wrong or if a question comes up while you're working, boom, there's somebody right there for you that you can ask the question to. Additionally, while I was doing office hours today, there were students we didn't break Zoom. Only 40 people showed up. We'll try again later in the quarter to see if we can get Zoom to break. But when there were 40 people on there, I was answering particular questions for a few people. And at the same time, students were helping each other in the chat in Zoom. And so there were questions being answered that I didn't even need to answer. So you can see all of the links for that in Canvas. Below that, you'll see our schedule, and a couple people have not realized that if you click on the number 1 or the date for week 1, that takes you to the list of things that you should be doing for week 1. In addition, before you click on that, on the right-hand side, you'll see that there is a to-do list. So there's going to be a lot of different ways that you can see what you should be working on each week. Right now, the instructors plan on having that type of structure set up for every week. So right now, all of the week 1 assignments are up, all of the week 1 due dates are up, and at the end of week 1, all of a sudden, you'll see all of the week 2 stuff start to populate in. Another thing that's good to use on Canvas, if you haven't been looking at the discussion boards, a student was asking about study tips, and there's a conversation on the discussion boards on Canvas about study tips, the best way to kind of structure your time and approach things. Some people like to do all their reading first. I think it's nice to kind of do a little reading, do a little bit of problem solving, and kind of move on from there. Okay, now we're getting into people asking questions. And the first question was being asked about the absorption lab prep activity. And the prep activity, the first problem in the prep activity 1 is probably one of the more confusing prep activities that we'll have this quarter, because we have to enter in a lot of data, and LabPal, in order to use the automatic feedback system, LabPal does a really good job with numerical data, not with written data, unless it's very specific words. So a lot of times when there's something where you need to have a word answer, we'll have some code for turning that word answer back into some numerical answer. So this first question is asking us to look at absorption in general, particularly for the PhET simulation that's linked at the top of the LabPal assignment, where there's a bunch of data about LabPal in there. Not about LabPal, about the assignment in there. So when you go through it all, you've got like 2 big text blocks that's also in the background of the absorption lab that you should also read. So the things you should do before you start trying these prep activities is you should read the background. You don't need to do the procedure, and there's a couple things that ask you to like print. You don't need to print things, but you should be taking notes of how you get right answers in your notebook. You should read the background. You should watch the videos that are relevant to the experiment. So that's going to be the Beer's Law defined. That's going to be the Beer's Law solving problems and the absorption lab video. The PhET simulation has us look at absorption for a couple different solutions. So you can go to the Beer's Law PhET simulation, and it gives you these different tools where you can have a solution, you can change which solution you're looking at, and you can, you've got a little laser and you can switch from fixed wavelength to variable wavelength. And when you switch to variable wavelength, you can move this little cursor back and forth, and you can see on the right-hand side, you got your laser on the left-hand side, and you've got your measurement device on the right-hand side, and you can kind of see how the absorption of light changes as you move that thing back and forth. At this point, I'm explaining things to people in the room looking at the PhET simulation, and I'm just letting the video catch up to where we actually start solving the problem. I was gonna try and have this thing where I could cut out this bit of the video, and maybe I will figure out how to do that in the future. But right now, I am not that good at doing video editing. Maybe by the end of this quarter, I'll become this expert video editor, but not yet. So the problem is asking us to explain some observed absorption phenomena. And when we think about absorption, we could kind of from the simulator, we can imagine making a plot either on paper or in our minds, where we create a axis system where we've got absorption value on the y-axis and wavelength on the x-axis. For wavelength, we're going to use the Greek letter lambda, lowercase lambda. And typically when we're looking at the visible spectrum, we're going to be looking at it in terms of nanometers. The visible spectrum is between 400 and 700 nanometers. And when we put different substances in the way of light, what we're going to have is we're essentially going to have a beam of light where we can change the wavelength of that light. And we'll see 4 different wavelengths of light. That material will have more absorption or less absorption or no absorption. At this point, you're all missing out. I was scrambling around the office hours. I think like 10 people left while I was doing this. I was looking for the Roy G. Biv spectrum with the actual wavelengths on it, and I couldn't find it. So I was rummaging through papers for a good 5 minutes there. I probably should cut this part out of the video, but again, this is a skill that I'll be learning throughout the quarter. If you're watching this, just skip through to where I'm writing again. I already tried cutting the audio once and it didn't go so great. So just skip past this part. Yeah, so I gave up on finding the piece of paper. So visible spectrum, right? And we're going to be focusing on visible spectroscopy for now. 700 nanometers is the long wavelength, which is going to be the short frequency and the low energy, and it's going to be on the red side. 400 nanometers is the high frequency, low wavelength, high energy side of the spectrum, and it's going to correspond to purple light. So here I am trying to divide into 6 even sections, and you can see I really didn't do a good job dividing into 6 even sections. So I went back with a blue pen and tried to do it again and got closer to 6 even sections representing red, orange, yellow, green, blue, purple. And then started labeling it in the wrong spot, realized as I got partway down and was like, oh, what did I do? And went back and fixed it. So red's down at the 700 side, orange is at the 650 range, yellow's at the 600, greens at the 580, blues at the 540, and then violets down in the or I guess I cut that a little wrong, but it's in the textbook. You can look it up. And what the first problem in the prep activity is asking us to do is essentially determine whether a peak is being, whether a color of light is being absorbed or not. So if you look at that red, you can see that the peak for that red is really not, the first peak is not really in the red section, it's over in the orange section. So we put a 0 underneath the red because it's not absorbing, a 1 underneath the orange because we've got that peak, a 1 underneath the blue because we got that peak. And the green, I put a question mark because we have a threshold for whether we consider it completely absorbing or not. And I can't remember that exact number now, but if you're reading the text block before the problem, it tells you if you have an absorption value above some number, count it as a peak in the spectrum. So I encourage you, as you're playing with that PhET simulation, to try and make a curve for what you think the absorption spectrum would look like. In the lab that we would have done, or if you go watch the absorption spectroscopy video, you'll see what you would have done in the lab where you actually see different chemical compounds absorbing light in different ways. Again, this is because it's easier for LabPal to make sense of numerical values. So if you just put a string of letters, it has trouble comparing that. So we convert the string of letters and where it's absorbing into a numerical map. That was enough to get everyone in the office hours at the time on the same page in terms of what they were supposed to do for that problem, I believe. Talking about whether that's actually an absorption peak or not. Wow, I wonder if anyone's going to watch this now that the audio and video is totally messed up. I think it'll go better once we get to some of the numerical problems. I really have no idea what I was saying during this part. Probably looking at the problems on LabPal and trying to figure out what the student's asking me about. Awkward. So awkward. Oh, I remember. Someone in the middle of me answering content questions, somebody asked me a question about due dates or discussion boards or something like that. And so I got distracted and was answering a question about Canvas, and that's why I'm not sure what I was talking about. I'll also have to go back and check if this audio is even picking it up enough. I don't know how good this microphone is. This is a lesson in how to make an awkward video recording of office hours more awkward by trying to record audio afterwards. With a microphone where you don't know how well it records the audio. I really gotta figure out how to cut these videos so I can have honestly, in the future, I'll have the audio with it so I can just upload it right away. I won't have to do this whole mess that I'm doing right now. Okay, here we go. Finally, we're moving on to a new problem. So someone in office hours was asking me about, let's see which question we're going to do. Going through the list of people asking questions. I'm asking them to read the problem to me. This was a really tricky problem. So this was on one of the mastery questions, and it was, I think, and it was asking us to convert, you've got a solution of HCl with a 33.94% by weight. The solution, when it's made, has a certain density. What is the molarity of the solution? And essentially, when we're looking at these types of problems, this problem is actually pretty complicated. It adds together a lot of different aspects. So if this problem looks a little bit confusing to you, go back, work on the practice problems, read through chapter 1 before you look at this problem. Someone in office hours was just ahead. One of the things that we have to realize is that when it's asking what is the molarity, we're looking for the moles of HCl per liter of solution. And then we have to think about how this information can lead us to that kind of idea, how we break apart the problem in terms of explicit information and implicit information. But that first thing of knowing that concentration is moles per liter is the first aspect. Now, in the problem, it gives us a little hint. It says, assume that the solution is 100 grams. It doesn't give us a mass of the solution. We've got percent by weight. But by using that 100 grams, we can essentially get the mass of the solution. The density is going to give us this relationship between volume and mass. That's going to get us the bottom half of the fraction. That percent by weight is going to get us the mass of HCl in the solution. And that's going to get us how much HCl there is. That's going to get us towards that number of moles. So once we realize those parts, we can start to realize how these different pieces of information, before we touch a calculator, we can start to kind of conceptualize the problem and figure out the pieces we need to find versus the pieces we are given to start with, and how those things can relate to each other. So I'll go ahead and I'll erase those blue parts, and I'll start actually working on the problem a little bit. Students reading something to me. 100 grams. This is the 100 grams realization. Since we're dealing with a 33.94% by weight, if we assume we have 100 grams total mass, that 33.94 will exactly give us the mass of HCl that we have. So we can now, by assuming, we could have assumed any mass, right? Since we've got a percent by weight, we could have done 1 gram and said we had 0.3394 grams of HCl. But when we get to pick our numbers, we always pick the easy things. And since it's a percentage, we're going to go with a 100 gram sample. That 100 gram sample, since we've got 100 grams, we know that 33.94 grams is going to be the HCl. First piece of information used. We can also use that second piece of information, the density. Since we now know the total grams of the solution, we can use the density to get between grams of sample and total volume of solution. So we're going to take that 100 grams of sample. We're going to divide by the density, right? We want that grams to be on bottom, that milliliters, that volume on top. grams of sample will cancel out. We'll get milliliters of sample. Since the density is a little bit greater than 1, we expect our volume in milliliters to be a little bit less than 100. Pulling out a calculator. Get your calculators out. You should be doing this problem along with the video. Your numbers are going to be slightly different, so you've got to do it for your numbers as well. You punch that into the calculator, and I'm reading off numbers as I punch them into the calculator. Probably made a mistake in the calculator. I think it's important to think about what numbers you should get before you punch them into a calculator. So you do your 100 gram sample divided by the density, that gets us your milliliters. Now, the way that I'm doing this, the way that I'm setting it up, is not necessarily the way that you solved it. This is the way that it makes sense to me, and that's what I'm demonstrating for you. So we've got our volume. That's going to give us the liters part of the molarity that we're trying to find. We still need to get the moles part. And so we have to think, well, what's going to be the piece of information that's missing that's going to get me from grams of HCl to moles of HCl when I've already got the 86.13 liters? That's right. If you were thinking, one of the students in the office hours answered and said, oh, it's going to be molar mass or molar weight. Molar mass, molar weight is this property of materials, kind of like density is a property of materials. It combines two of our measurement phenomena. So we can use molar mass to convert grams to moles. Now this gets into this idea of explicitly given information versus implied information. The percent by weight, the density, that was explicitly given to us. The problem assumed we would be able to figure out this idea that we would need molar mass, which is units of grams of compound per mole of compound. We'd be able to figure out what the molar mass is in order to convert our HCl from grams to moles. And to do this, we need a periodic table, of course. So you get your periodic table out, go to the Canvas page, and inside the modules, you've got the periodic table with useful constants there. You look at the mass of HCl or the mass of chlorine plus the mass of hydrogen, and you get how many grams of HCl it would take to get 1 mole of HCl. This was not given in the problem. The problem assumes that we can figure this out. It's what I call implied information, or information that you need to infer from the problem, not explicit information. So this gives us our next step. We can now take from our 100 gram sample, we can take the 33.94 grams of HCl. We can use that molar mass, dividing by the molar mass, or what I like to do is multiply by the reciprocal. So we get our 1 mole on top, and we're going to cancel the grams of HCl. Notice I like to explicitly write. I don't like to just write grams. I like to write grams of sample. I like to write grams of HCl. One of the biggest problems we have in chemistry is being consistent with our units. And when we say grams, we have to say which material we're looking at for our grams. So I like to be explicit. Out of that calculation, we can see, since it's 33.94 grams of sample and it's 36.46 gram molar mass, we get something that's just a little bit less than 1 mole of HCl in our sample. Now, we're not done, because the problem isn't asking for how many moles of HCl we have. It's asking for our molarity of HCl. So we've got to take that number of moles we just solved for. That's going to be the top of the molarity. And then we've got to take our total volume of sample, and that's going to be the bottom of that fraction. Notice, though, if we're looking at the units of molarity, it wants it in moles per liter. So I'm going to take that 0.931 moles of HCl, and I'm going to divide by the volume converted to liters of sample. And you notice I did the conversion from milliliters to liters in my head. It's dividing by 1,000. So 86 becomes 0.08 0.086, 3 decimal places different. When you do that calculation, you get the right answer, hopefully. Your numbers when you're doing this in LabPal will of course be different than the numbers I did it for, but the process should be the same. Always make sure you pay attention to what units the problem is asking for the answer in, because that changes for each problem. I'm probably reasserting the idea of explicit information versus implicit information and how we can kind of think about the problem before we actually start calculating the problem. Going over kind of all of the thought processes. This was a kind of long problem and we had multiple steps, talking about how we use the information we're given, how we figure out what we need to get our answer in, and then figuring out what that missing piece of information that the problem is assuming we know, or that the problem is asking us to use. Oh, I was checking who had the next question. I've got to do something about my wardrobe. Oh, there was a question that somebody asked, and the reason I made that face was because apparently in the mastery questions, and I've got to talk to Dr. Campbell about this, but apparently in the master questions, there's a question about the photoelectric effect. And that is for next week, and so I've got to check in with Dr. Campbell and make sure that we figure out if that was a question, because I think it relates to the emissions lab and stuff from chapter 3. And so I think I've got a note to self, talk to Dr. Campbell and check on that. So that's probably what I'm looking at now. That's why I've got such a weird, confused face. But just in a moment here, we'll get to another decent problem. I didn't realize the video was having trouble focusing. Funny. Still talking about trying to figure out whether that question should have been on there or not. Probably made a note to myself. Honestly, no idea what I'm talking about. Even though it was just like an hour ago, I don't remember. But finally, we're moving on to the next problem. Okay, so this was, I don't remember where this problem is, but this is about the thickness of a piece of aluminum foil. And it's kind of this idea that's important to chemistry, where when you look at a piece of paper, we think of it as having no thickness because it's so thin. But when we start looking at things on the atomic scale, it actually matters that it's not, on the atomic scale, it does have some necessary thickness. So we can think of a thin sheet of aluminum or a thin piece of paper, and we can think about which dimensions are easily measurable and which dimensions are more difficult to measure. So for example, on a piece of paper, it's pretty easy to measure the width and the height, measuring the two dimensions that are easy, but the thickness of it is really hard to measure. So we can instead crumble it up measure the mass of the piece of paper or the volume associated with the piece of paper by using density. So again, we're using one of our properties of material to get between the idea of something that's easy to measure and something that's difficult to measure. So our problem is really looking at this combination of the idea of mass and volume. And this is all thinking we can do just when we first read the problem before we start looking at the numbers. Then the students going ahead and reading the specific numbers they have, they get something that is 11.1 inches by 11.2 inches. It weighs 5.2 grams. And since the material we're looking at is aluminum, it has a density of 2.7 grams per centimeter cubed. So already we can see that density plays a role here because we're looking at a measured mass versus a total volume. We know two of the sides, the 11.2, the 11.1, and we have to figure out what that thickness is. I believe I call it height later on, but we have to figure out that one aspect there, that how thick is a piece of aluminum foil. Knowing that mass and volume is why we've got density. Just thinking through it. So the way that we can think about this is we can say, well, we've got density, we've got this unit of centimeters cubed. We can see that we can get the total volume of the piece of aluminum foil by relating grams of sample to density, dividing by the density, so grams cancels out. And before we hit our calculator, we can see that 2.7, that's like 2.5, so we should expect to get something that's like a volume around 2. Right? We've got our grams of aluminum, again, specifically writing aluminum there to keep our units clear. Our 1 centimeter cubed per 2.7 grams of aluminum, multiplying by the reciprocal, similar to dividing, but I like it the way it makes the unit cancellation line up a little bit better. And we should get something that's a little bit less than 2. 5.2 divided by 2.7 equals 1.93 centimeters cubed. So again, I picked the unit that seemed more simple, so I picked the mass to convert first. This is the way I approach the problem. We could have done it a couple different ways. Centimeter cubed is a unit of volume. It defines 1 milliliter, but this problem is actually asking us to find the height in terms of millimeters. So it turns out we don't actually need that milliliter conversion in this case. That pause there was me asking the student what units the problem was asking the answer to be put in. So while that's a good definition to have in our head, we didn't need it for this problem. Instead, we can go ahead and think about how volume relates to, how the volume we have for our aluminum relates to the shape of this particular piece of aluminum. So we're going to have width times length times height, or thickness, and we know that's going to be the volume. Now, for the numbers we have, we would have 11.1 times 11.2 times our unknown height is equal to 1.93 centimeters cubed. And this equation that I just wrote down should make you cringe a little bit. And that's what I'm saying right now. Because our units don't match up. We've got inches, inches, and centimeter cubed with an unknown that we want in millimeters. So that equation is kind of actually a bit of a mess. Now there's a couple different ways we could have gone about fixing it. We could have converted the centimeters cubed into inches cubed, or we could have gone about converting everything into millimeters. I decided to go with the idea of converting inches into centimeters, so that way I can handle my conversions one at a time. And the idea is that I get centimeters for the unit of width, centimeters for the unit of length, and centimeters for the unit of height. So that way I get centimeters overall, centimeters cubed overall. Oh, so go to the Canvas page. You can find the equation sheet there. All kinds of useful information. One of those useful bits of information is the conversion between inches and centimeters. So 1.1 inch, you've got 2.54 centimeters for 1 inch. Noticing that we make it so the inch part is on bottom to cancel out the inches, and we can get our unit in centimeters. We're going to do the same thing for the other dimension. So notice, because this is a multi-dimensional object, it's a three-dimensional object, I actually have to use that conversion multiple times. This is where sometimes you'll see like a unit conversion squared. I did it in 2 separate steps here. I did each dimension individually. Since it's 11 times about 2.5, you get something that's a little bit more than 25. You get 28. 11.2 is a little bit bigger than that. You get 28. Let's see. Calculator says, again, do this on your own. Your numbers are going to be slightly different, but the process should be the same. .45 centimeters. Almost the same, a little bit different. 11.1 versus 11.2. Now you'll notice we've got units of centimeters. Units of centimeters. Our unknown height will also be in units of centimeters, giving us centimeters cubed. All of the units end up working out. We have to be careful though, because the answer is asking for the final answer wants it in different units. But we'll first solve for this thickness, the height of this rectangle, in terms of centimeters. What am I even saying now? Oh, I know what I'm saying. Okay, so one of the things that we want to think about is kind of our expectation of answers, right? We should always think about our expectation of answer. And here, you'll notice that the total volume is much smaller than the 2 dimensions we have. And that's because the thickness of this aluminum foil, or if you want to think about it in terms of a piece of paper, the thickness is really small. So we're expecting a small number divided by a large number to give us a very small number, because a piece of paper or a piece of aluminum foil is so thin. So you do 1.93 centimeters divided by the 28.19 times the 28.45. You'll notice that the centimeters units, because we were careful with our units, centimeters cancels out, and 2 of the centimeters cancels out, and we're left with units of centimeters of 0.00241 centimeters, a very thin piece of paper, or sorry, piece of aluminum foil in this case. Now, the problem is asking for this in millimeters, so we have to go ahead and use our conversion. You could convert centimeters to meters and then meters back to millimeters, but just with a little mathematical manipulation, you can figure out that there's 10 millimeters for every 1 centimeter, which gives us a final answer of 0.0241 millimeters. Very thin piece of aluminum foil. Hopefully, this dubbed over problem solving is still being somewhat useful, even though it's very awkward for me. Moving on to the next question, I'm figuring out whose hand is next in order. There's a nice function in Canvas where, not Canvas, in Zoom, where if you click on participants, you can raise your hand and it'll actually put you in order from when you raised your hand, so I can keep track of who's next in queue for getting questions answered. It's problematic if there are people who have questions about the process I'm in at that time. Raising your hand doesn't jump you to the top of the queue. Don't know what I'm talking about here. No clue. One of the things that's going to be really awkward about all of these videos is I'm using my laptop camera and then a webcam for one for doing the recording for posting to YouTube and one for Zoom, and they are at different heights so they don't interfere with each other, but it makes it so I have to get down low for the Zoom camera and up high for the recording. So moving on to the next problem, if I remember correctly, this one was about distance traveled for some object, or not distance traveled, how long it takes for light to travel from a distant star to us. And so one of the things that we need to know, again, off of the equation sheet, is the fact that we've got a speed of 2.99 times 10 to the 8th meters per second. That autofocus is bugging me. So we go ahead. This was a interesting thing. The distance to the star was given with I think maximum digits that LabPal can create. So my guess is this is what happens when you don't use the round function in LabPal. There's a bunch of math commands, and if you just say make a random number, it makes it with like 10 decimal places. So I went ahead and I said let's just round, even if we round down to 4 decimal places, so it's 7.4749, and it's not actually 10 to the 16. The student misspoke, and I'll fix that in a moment. It's 10 to the 15, but even with that rounding, we're still going to only be introducing a 0.01% error. So we're not going to be introducing a lot of error in this case. You'll notice the problem here is we've got two distances. We've got meters and we've got miles, and then we've got seconds. And again, the problem is asking for how long it takes in terms of number of years. So there's this kind of thought process we have to do in terms of what's the explicit information given and what's the implicit information that we need in order to get between these things. So again, there are different ways to approach this problem, different ways that we could calculate this. For me, rather than converting the speed of light to miles per year, I thought it would be easier to convert miles to meters and figure out how many seconds it was traveling for. So I grabbed the equation sheet and I found the conversion factor on there to get between miles and kilometers, which was 1 kilometer is 0.626137 miles. And then I want it in meters since the speed of light I have is in meters, so that's 1,000 meters per kilometer. And that will give me the total amount of meters distance to this distant star, noticing that the units cancel. I've got it set up so miles will cancel out, kilometers will cancel out. And with those units, I should expect a number close to 7. Well, no, actually, because it's divided by a third. So let's see what calculator's out. We'll do the calculation. And this was where the correction came in. It's actually 10 to the 15. For your problem in LabPal, you're going to have your own calculation that you need to do because the numbers are randomly generated for each student. But the process is the same, and the thinking behind the problem is the same. We've got our distance traveled, 1.203. Notice I did a bunch of rounding, didn't need all those digits. I mean, I am introducing some error by rounding, but with the number of digits I kept, I'm probably introducing a small amount of error. So 1.203 times 10 to the 19 meters is the number of meters. That is the distance to this distant star that we're trying to figure out how long it takes for light to travel there. So then we use the speed of light multiplying by the inverse or dividing by the speed of light so we can cancel out our number of meters and get to seconds. Notice speed becomes like our other material properties from problems earlier in the office hours. It allows us to convert from one measurement property to another measurement property. In this case, we're switching from a distance to a time. Oh, that was where the student told me they were doing it a completely different way. They were working on converting the speed of light, and while that method works, I find there's more ways that you can mess up. Since the speed of light has 2 units inside of it, there's just more opportunities for making a mistake, which is why I'm doing it this way. Again, there are multiple ways to do a problem, and this was just the way that worked best in my head. And that's why I'm demonstrating it to you. So we get our time in seconds of 4.023 times 10 to the 10 seconds. Huge number of seconds. No idea what that means in terms of an amount of time, besides it's a lot. So this is also where we have to convert to years, and I make a typo in this problem as I do the conversion. See if you can catch it before I do. We got our seconds. We got 1 minute is 60 seconds, so that will get us to number of minutes. Then we've got 60 minutes in an hour, 24 hours in a day, and 365 days in a year. Did you catch the typo? It's already happened. You can see as I'm trying to cancel units, I realize something's wrong. Buying time by finishing writing year. Got it. Ah, there it is. I totally, even though I have the right conversion factor, I have it flipped over, and it made it so I flipped everything over. I had minutes times minutes on top. When I want minutes divided by minutes, I want that unit to cancel out. And that one mistake I made it so I ended up flipping the rest of my conversion factors, my conversions for time, and it would have thrown off my answer entirely. So we've got to be careful about going too fast. Now you'll notice seconds cancels, minutes cancels, hours cancel, days cancel, and we get something that's just in terms of years. That one flip I made there, as soon as I started trying to calculate it, I realized there was a problem. But all of our units cancel out now, and we're going to be left with something just in terms of years. $1,275.6 years. That is the amount of time it would take for light to travel from some distant star to Earth. At this point, most people left office hours, and there weren't any other questions, so I went ahead and stopped the video. You'll notice all of the problems. Sorry about the audio hiccups. I hope this video is tolerable with the voiceover going on. I imagine it'll be pretty jarring. I'll be making another video on office hours tomorrow, and I figured out how to do the audio correctly, so that problem won't happen in the future. If you haven't started working on the lab, there were several students concerned because they were like, this lab isn't making sense to me. Why isn't anyone else asking questions about lab? And it turned out that no one else in office hours had started the lab yet. So if you haven't started the lab, I would strongly encourage you to start the lab, so that way you can ask questions before it's due on Friday. Okay. Hopefully this was helpful. Hopefully this was tolerable. I'll try to do better in the future. And I will learn how to edit videos sometime soon. Thanks, everybody.